Okay, so here comes probably the most important topic that we will go over this entire semester, and this is the transmembrane potential. This is something that will carry through into the next unit. It will carry through into A&P2. It's really important basic information. I say basic, it's not that super basic, it's actually, it's a little bit complex, but it's very interesting, and if you just spend the time on it, it's easy to understand. You just have to keep it straight and organized in your mind, and it'll eventually become second nature to you, and that is the goal here for this. This is one of those topics that's just going to keep coming up, and it's really the basis behind everything you do in your body. So anytime your neurons have an action potential or don't have an action potential, anytime your muscles contract, anytime a gland secretes, it has to do with this membrane potential. And what this transmembrane potential is a difference in charge across the cell membrane. So the way I am going to be drawing it is, here's the cell membrane. This will be outside the cell. Let's put outside. And then in here will be inside the cell. So what we need to remember before we get into this is to remember that the cell membrane is a separation between the interstitial fluid outside and the cytoplasm inside the cell. So we have an outside environment of fluid and we have an inside environment of fluid. Now, water can pass easily across this cell membrane, but ions cannot pass that easily across the cell membrane. So let's just assume for right now that they can't move at all. So that's not exactly true, but let's just assume it for now so we can set up a situation, just a snapshot of what's happening when the cell is at resting. Now, this is a neuron that we're drawing out here. So it's typical resting membrane potential. So when the cell is not being stimulated, that's what I mean by resting membrane potential. It's just kind of sitting there, nothing's happening to it. A typical resting membrane potential is negative 70 millivolts. That means that it is negative or 70 millivolts less charge in here than it is out here. And this is just a general number. It might be negative 65, it might be negative 60. It's different for each particular cell, but generally about negative 70. Okay, so we're going to worry about, well, 4 ions. We'll do 4 ions here. The first one is sodium. We have a good deal of sodium outside the cell. So we have a lot of sodium outside the cell. We have sodium inside the cell, but not so much, so I'm just not going to put it there just to contrast. So lots of sodium outside, not so much inside. Potassium, let's put some potassium. We will have a lot of potassium inside the cell, not so much potassium outside the cell. Of course, there's potassium out there, not as much as compared to inside, so I just will leave it off to keep it simple. So lots of sodium outside, lots of potassium inside. Chlorine. We need to put some chlorine here. We have a lot of chlorine outside the cell and not so much inside the cell. And then for our last one, calcium. Let's put that above because we're going to leave calcium alone for a while after we do that. A lot of calcium outside the cell, not so much calcium inside the cell. So this is just the general way it is when a cell is at rest. You have lots of sodium, lots of chlorine, lots of calcium outside the cell. Inside the cell you have lots of potassium. You also have lots of things like proteins, which have a negative charge on them. Inside the cell there will be other ions. We don't need to think about all of the ones that would be inside the cell. Just really the potassium is what we're worried about. And the proteins because of the negative charge, to keep it negative 70 inside here. So we have a negative environment here inside, and we have a positive environment here. So they're opposite. They are polar opposites, if you will. So we could call this polarized. The cell is polarized because it's positive outside, negative inside. There's a big difference in charge. 70 millivolts to be exact. So polarized. Okay. Now we know that it is not really realistic to think that this is just going to stay here, and if it did, then well, you wouldn't do anything. You couldn't think, you couldn't contract your muscles, your heart wouldn't beat, nothing would ever happen if we couldn't move these ions across the cell membrane. And we know that they do, and we know that they need protein channels that are embedded in the cell membrane that allow the ion to move across. So these protein channels, or we could call them ion channels, they'll be specific for each particular ion. So we'll have sodium channels that sodium can move through. There will be potassium channels that potassium can move through. There will be chlorine channels for chlorine to move through. And there will be calcium channels. Let's not worry about those right now. There'll be channels for every ion, so we don't need to include them all. These are the three that we're really going to focus on. Okay, so now, these channels are going to be one kind of many. So there's different options for what kind of channel this might be. It's always going to be specific for the ion, but it could be something called a leak channel. A leak channel is always open. So it's going to allow ions to leak across the membrane in whatever direction they're being pushed to do so, which we're going to get into that. It's called the electrochemical gradient. They're going to be moving with their gradient across the leak channels, or across the membrane, using the leak channel to get across the membrane. So these leak channels will just be constantly allowing movement of ions in and out of the cell in whichever direction they're being pushed to go. Now we also have gated channels, and gated channels require a stimulus to open. So something has to happen in order for these to open, but once they do, then they'll open and they'll allow the ion to move across, whichever ion it might be. So it might be a sodium gated channel, and when it opens it'll allow sodium to move through. It might be a potassium gated channel, which when it opens it'll allow potassium to move through. So they'll still be specific for the ion, but you'll need to do something in order to open them. And these can be categorized based on what exactly you need to do in order to open them. So there are mechanically gated channels. Mechanically gated channels open to a mechanical stimulus, like they say. So some sort of distortion of the cell membrane. So literally pushing on the cell membrane, so I'm going to push on the outside. So you push and it opens the channel. So your touch receptors, for example, would have mechanically gated channels. So here's my skin, there's a touch receptor right there, and I push, and when I'm indenting my skin like that, I'm indenting all those cell membranes, and those touch receptors have these mechanically gated channels, and they open, and there'll be sodium channels in this case, so we'll allow sodium to move, and that will cause me to know that I touched my hand. There are also chemically gated channels. Chemically gated channels are also called ligand gated channels, and they require a chemical stimulus to open. Now an example of that, I'm trying to find the picture that we had before, would be when we release neurotransmitter. Where's that picture? I'll have to draw it again. So we release neurotransmitter into a synapse. So I'm just going to draw that real quick right here, up here. So neurotransmitter comes into the synapse. There's the second neuron. There's the receptor for the neurotransmitter. When that neurotransmitter binds to the receptor, that receptor could be a chemically gated channel, which would cause an ion channel to open. And that is one way that neurotransmitters work. Sometimes they work just by binding right to a chemically gated channel. Then we also have voltage gated channels, which we will get into the details of those later, but these require a specific electrical stimulus called threshold. So it has to be a strong enough electrical stimulus, which is called threshold. It's a very specific number for each voltage gated channel. And if you get that electrical stimulus, you'll open that channel. Okay, now these two are found primarily on the dendrites, the dendritic spines, the somas of the cell. They're also found on the axon, but they're not the predominant channel type that are found on the axon. The important channel type that are found on the axon are the voltage-gated channels. And they'll go from the axons all the way down to the telodendria to the synaptic knobs. These are responsible for action potentials. These are responsible for something else called graded potentials, which we'll get to in a bit. But first, what we want to do is think about when we open these channels, what directions the ions are going to go. So we'll leave this picture in the background and we'll go into electrochemical gradients, which is going to determine whether an ion is going to go into the cell or out of the cell. So an electrochemical gradient is going to be the push, the force that causes an ion to move. And it is the sum of the electrical gradient of that ion and the chemical gradient of that ion. So you need to know what those two things are in order to figure out what the electrochemical gradient is. So the electrical gradient just means that opposite charges attract. Negative ions want to be where it's positive, and positive ions want to be where it's negative. And then vice versa, like charges repel. So a positive ion does not like it when it's in a positive situation, and a negative ion will be repelled by being in a negative situation. Now the chemical gradient has to do with ions needing to move from a high concentration of themselves to a lower concentration. And we saw this with diffusion when we had, say, a lot of sodium on one side of a semi-permeable membrane and not so much sodium on the other side. The sodium moved across that membrane until it was in equilibrium, right? So until, like, say, we had the same amount of sodium ions on either side. That is the chemical gradient. So you already know that. So let's look at our situation at resting, so that if we opened a channel for any of these ions, well, for the three, for sodium, potassium, and chlorine, which direction they'll be. So think along with me as we do this, and see if you can guess what I'm about to write in this chart. We'll do sodium first. So the electrical gradient for sodium, remember here we're looking for opposite charges attracting. It's negative inside here, inside the cell. It's positive outside the cell. Remember that, negative inside, positive outside. Sodium is a positive ion, so does it want to go into the cell or does it want to stay out of the cell? And if we were in class, this is where you would all go inside the cell. Wants to go inside the cell. So sodium is drawn to go inside the cell electrically. Chemically speaking, ions move from high concentration to low. We have a high concentration of sodium out here, a low concentration of sodium inside here. So which way does sodium want to go? Does it want to stay outside where there's a lot of it, or does it want to go inside where there's not so much of it? And again, inside is the answer there. It wants to go from high concentration to low. So this one is easy. When you add these two up, they both agree. The electrical gradient tells sodium to go inside, the chemical gradient tells sodium to go inside the cell. So the electrochemical gradient for sodium is to go inside the cell, and it's a really strong gradient. Sodium really, really, really wants to go inside the cell. So let's draw that out here. Sodium wants into the cell. Okay, so let's do potassium. Potassium, positive ion, negative inside, positive outside. So electrically speaking, where does potassium want to go? Does it want to stay inside the cell where it's negative, or does it want to go outside the cell where it's positive? Well, it's a positive ion, so electrically speaking, it's happy. So potassium wants to stay inside electrically. Chemically, though, where ions want to go from a high concentration to a low, potassium is in a high concentration outside the cell, low concentration, or I'm sorry, it's a high concentration inside the cell, low concentration outside the cell. So chemically speaking, potassium wants out. It wants to go from the high to the low. So outside. So when you go to add these two up, that doesn't seem quite as easy because they're conflicting. One, the electrical gradient is telling potassium to stay inside. The second one, the chemical gradient, is telling potassium to leave the cell, to go outside. So which one wins? Which one is stronger? In the case of potassium, the chemical gradient is the stronger one. So the push for potassium is to go outside. Now, it's weaker of a gradient than what sodium's is, to go inside, because these two don't agree. There is a bit of a draw for potassium to stay inside. It's just that at resting membrane potential, potassium has a bit more of a chemical urge or a chemical push to go outside than the electrical push to stay inside. Okay, so let's do it for chlorine too. Remember, negative inside, positive outside. Chlorine is a negative ion with a high concentration on the outside. So electrically speaking, chlorine is happy. It's negative, it's outside where it's positive, so outside, electrically speaking, for chlorine. Chemically speaking, high concentration outside the cell, low concentration inside the cell. Chlorine wants to go inside the cell if looking only from the chemical point of view. And again, we have a situation where these two balance, or where these two are conflicting with each other. So electrically, it wants to go outside or stay outside. Chemically, it wants to go inside. So which one wins in this case? In this particular case, they are exactly equal at resting membrane potential. The push to stay outside is the same as the push to go inside, so nothing happens. It is at equilibrium. And this would be called the Nernst potential, which we'll get to in 1 second. We'll tie some things up and then we'll get to that. But there is no net movement in either direction. So let's fill out our potassium and our chlorine here. So potassium, we open up the channel. When we open the channel, we allow potassium to move. Potassium will go out. For chlorine, we open the channel. It's at equilibrium. It doesn't want to go anywhere. It just doesn't care where it goes. So a little bit goes in, a little bit goes out. That's equilibrium. No net movement. So we don't have a change in concentration in either direction. Okay, so one thing to note, or a couple things to note. When an ion moves, it takes its charge with it, which is going to affect the whole -70 situation. So when you allow ions to move, you're changing the electrical charge here. So for example, when sodium comes into the cell, sodium has a positive charge, and it brings that positive charge with it, and it diffuses along the cell membrane. So we're going to be making this less negative here. We're going to be making it less polarized. So we would be depolarizing. Now in this case with potassium, when potassium is moving out, it's taking a positive charge out of the cell. That leaves a negative charge in its wake, and that negative charge will diffuse likewise across the cell membrane, and that is called hyperpolarizing. Now a chlorine channel, because it's at equilibrium at -70, if this membrane is at -70, chlorine isn't going to be doing any kind of depolarizing or hyperpolarizing or anything. It's not going to be moving in or out of the cell at any particular rate. So it's not going to change the charge on the cell membrane. An exception now is if we were to depolarize the cell. So let's open a sodium channel right next to that chlorine channel, and we get positive charges. And let's say it's now -50 millivolts inside the cell there. Now chlorine is no longer in equilibrium. We have changed this. So the electrical gradient weakens because it's no longer as negative inside, while the chemical gradient stays the same. It's just the same strength as it was. It just doesn't have that same strength of an electrical gradient to balance it out. So chlorine then would come in, but only until it completely negated whatever depolarization you'd already done. So only until you got it back to -70 millivolts. And then once it's at -70 millivolts, we're back to equilibrium again, and chlorine won't come in anymore. What we call this is repolarization, because it can put you back to your resting potential, but it cannot make you more negative than your resting potential. Okay? Okay, so what we saw here, what we left off, was talking about the Nernst potential for chlorine. So the Nernst potential for chlorine is negative 70 millivolts. And this Nernst potential, the definition for it, is the charge at which an ion is in equilibrium and there is no net movement across the membrane. So we saw that Nernst potential for chlorine being negative 70, and chlorine wouldn't come in really. It didn't really care which way it was going at negative 70. But if we made it more positive inside the cell, so we put it to say negative 50, now chlorine does come into the cell and brings it back until it's in equilibrium again at negative 70. But all of these ions have their own Nernst potential. So there will be a charge at which sodium no longer wants to come into the cell. So it'll be too positive in here for sodium to want to come into the cell. And that particular charge is positive 66. So at positive 66, if this membrane was at positive 66 millivolts, that's the charge where the electrical repelling, with it being so positive inside, would be equal to the chemical push for sodium to go in, and sodium would no longer enter the cell. This is not something that is typically going to happen in everyday life. It's not something you would want to happen because you need sodium to come into the cell in order to do anything. So this isn't really a realistic sort of potential to have happen to you. Now for potassium, the Nernst potential is negative 90 millivolts. So when potassium leaves and it gets it to be more negative, it can get it to be as negative as negative 90 millivolts, and then it'll stop moving out, because then it's, you know, perfectly in electrical and chemical balance at negative 90 millivolts. So in this case, this is pretty close to resting potential. Resting potential is negative 70. The Nernst potential for potassium is negative 90. And when we are recovering from an action potential, we always get to negative 90 millivolts. And that is what makes potassium stop leaking out in that case. So we do reach that all the time. And obviously, we're mostly in Nernst potential for chlorine until something happens to throw us off at that equilibrium there. Okay? Okay, so let's take our little break here from this video because it's dragging on, and we are going to pick up thinking about this little depolarizing here when we allowed sodium to move in, and the hyperpolarizing when we allowed potassium to move in, and then the chlorine coming in to negate a depolarizing. So that'll be our next video.